Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss the classification of hydraulic turbines. So, the hydraulic turbines are classified into many categories. The first one is according to the type of energy at the inlet condition, and second one is according to the direction of flow through the runner or through the vents, also can be called, according to the head at the inlet of a turbine, according to the specific speed of a turbine. So previous classes we have seen that head of turbines and what is the working principle of hydroelectric power plants. Okay, so many things we have discussed in our previous lectures. Now we'll see different types of turbines. As I told you, the hydraulic turbines are divided into based on the categories like energy of the inlet. So first, this according to the type of energy at inlet, it's categorized into two types. One is impulse turbine, another one is reaction turbine. So similarly, according to the direction of flow through the runner or through the vanes, it is categorized into four types. One is tangential flow turbine, radial flow turbine, axial flow turbine, and mixed flow turbine. Similarly, according to the head at inlet of the turbine is categorized into three types: high head turbine, medium head turbine, and low head turbine. Similarly, according to the specific speed of the turbine, it is categorized into three types: low specific speed, medium specific speed, and high specific speed of the turbine. So we'll discuss one by one all these turbines. First, we'll see impulse turbine. The impulse turbine actually, uh, this one, this impulse turbine actually, if the inlet of the turbine, if at the inlet of the, suppose this is one example, actually this is an exact example of impulse turbine. So let me tell you first, at inlet of the turbine, the energy, at inlet of the turbine, the energy which is available, only kinetic energy, the energy available at inlet, that is kinetic energy. Okay, then that kind of turbine is known as impulse turbine. Okay, so what is the meaning of energy available at kinetic energy will be available at the inlet will be kinetic energy at inlet, it should be kinetic energy. Now this is one example. Okay, in this impulse turbine we have some different kind of turbines are taken in this, like one of them is Pelton turbine, is there, and uh, another one is like Banky turbine is there, and Zonewall turbine is there, and many more options are there actually. So out of all these turbines, this is the most useful turbine in the impulse one, Pelton turbine. Mostly we used to refer the Pelton turbine as a impulse, like mostly it used to work normally. These are things that must not be considered. So the Pelton turbine actually, if you see, so this is an example of Pelton turbine, or this is the structure or exact structure of Pelton turbine we can see. Now, in our previous lecture we have seen the water is to store in a dam, okay, and from the dam, like suppose the dam is there, and from the dam the pipe is connected to this, and the long pipe is called penstock, and through this pipe the water used to flow inside this one, and at this end of the pipe a nozzle is connected, and because to increase the velocity of the jet, so that the fluid will come with a jet speed and it will strike the vents. These are the vents or blades which is called. Then the runner will start rotating, and the runner is fitted in a shaft. The shaft also started rotating. Now here, as per the energy as I told you, so when the water is flowing through the pipe, okay, we know that it will have, so if when it is stored in the container or in a dam, it is to have a potential energy is there, okay, but when it started flowing, even pressure energy also will be there. When it started flowing inside a pipe, okay, it is to have the kinetic energy as well as the pressure energy. But when it is coming out in the nozzle, all this pressure energy will be converted to the kinetic energy. So the water which is, as I told you, if at the inlet of the turbine, okay, the energy available, the energy which is coming out, okay, this is inlet of the turbine, correct. So the pressure energy also converted to kinetic energy, and the energy available at the inlet of this turbine is only kinetic energy. That kind of turbine is called impulse turbine. Okay, so this is the same one, because Yeah, because and the pressure energy, as I told you, it is converting to the kinetic energy. So only kinetic energy is present at the inlet of the turbine. That is impulse turbine. Similarly, the reaction turbine is actually here in the reaction turbine. It used to have slightly different. Here, as I told you, that only kinetic energy is there, but in the reaction turbine, it is not like that. Okay. Because see, in the impulse turbine also, you can see the water started flowing here over the vanes, and the pressure will be there atmospheric from the inlet to outlet. This is the inlet condition, and outlet of this means outlet of the turbine, the atmospheric pressure will be impacted on this. So that will discuss while we'll discuss the Pelton wheel, we'll discuss in that. Now reaction turbine actually, if the inlet of the turbine, okay, at the inlet of the turbine, you can say at the inlet of turbine, the water possesses kinetic energy as well as pressure energy. The water possesses kinetic energy as well as pressure energy. Then that kind of turbine is known as reaction turbine. Okay. And what are the example of this reaction turbine? So reaction turbine example is like Francis. This is Francis turbine, and propeller turbine, and Kaplan turbine. Okay, and Thomson turbine also there. Thomson turbine, and many more examples are there actually. In that, mostly it used to use like Francis turbine and Kaplan turbine, sometimes propeller turbine also. Okay, the reaction turbine actually, as I told you, that at the entry part, of the inlet, okay, we can say a part of energy, because I told you that the total energy like kinetic energy and pressure energy both will be there. So a part of energy is converted to, obviously, the total energy which is present here. So few part of the energy is converted to here kinetic energy. See, this is not the example of reaction turbine. Just I'm showing you how it is to work actually, because that construction is different. Okay, let me show you. Yeah, if you see here, this one is the one example of Francis turbine, or you can say reaction turbine. This is also even a reaction turbine, because reaction turbine working principle is different and their construction is also different. Okay, just to keep in mind that when the water is to come inside, okay, so along with the kinetic energy, the pressure energy also present in that. Okay, that we'll see when we will discuss the working principle. We can understand more in details. Okay, and as I told you that few part of this water is converted to kinetic energy, and maximum part also remains as usual the pressure energy. So both kinetic energy and pressure energy will be act at the inlet of the turbine. Okay, and here one more thing here, the pressure at the inlet condition, always the pressure at the inlet condition will be always higher than the pressure at the outlet condition. Okay, so that what we can say, the runner, due to this the runner actually used to always completely airtighting, and the runner and casing is completely full of water. Due to this difference pressure, the inlet and pressure of the outlet, okay, the runner is completely enclosed in a tight casing. So that we'll discuss in details later. And the runner and casing both are completely within the water. Here it is not like that. Water striking here, after striking it started rotating, and the water falls here in the tail race, you can say. And next is, I can say that the difference of pressure, what I told you, the difference of pressure at the inlet and outlet of the runner is called reaction pressure. Is called another one terminology actually, reaction pressure. The difference of pressure at the inlet and outlet condition is called reaction pressure, and the turbine is called, that's why, reaction turbine. That's why the turbine is called reaction turbine. I hope you understand. Okay, the next one is according to the direction of the flow through the runner. Now according to the direction of flow through the runner is nothing but first one, as I told you, tangential flow direction or tangential flow turbine. So tangential flow turbine actually, if you see, the water flows here. One example I'll tell directly. This is the tangential flow turbine. So example of this is Pelton turbine or Pelton wheel turbine. So here at the tangential flow turbine, the water flows along the tangent to the path of rotation of the runner. Okay, now see this striking here, the water is striking here tangentially. So as the runner started moving, so it's acting only tangential direction. If you take this bend, this is tangential direction. So this water strikes here, the water flows along the tangent to the path of a rotation of the runner. That's why it is called tangential flow turbine. Example of this is Pelton turbine. Similarly, radial flow turbine. Radial flow turbine actually, in this, the water flows along the radial direction. Obviously, this is tangential direction and here it will be radial direction. This is, the flow will be in the radial direction and it remains, okay, the partially or you can say substantially in the plane normal to the axis of the rotation. Okay, when the axis of rotation will be there, it is passes through the runner. And the radial turbine actually it is in categorized into two types. Okay, one is inward radial flow turbine, another one is outward radial flow turbine. Two turbines are there, one is inward radial flow, another one is outward radial flow. So inward radial flow actually, if you discuss about the inward radial flow turbine, this is nothing but the water enters to the turbine, okay, from outside to inside, from outside to inside. From outside to inside means outside to inside of the inside flows radially and it will move to the centers. Now, what are the examples of this? Example is nothing but old Francis turbine. So here the example I can consider here, old Francis turbine, and even Thomson turbine also is coming under this. Thomson turbine and Girard turbine is also there. So these are some different types of turbines coming under inward radial flow turbine, and mostly that old Francis turbine is to use. Now I'll show you. So this is one Francis turbine. Okay, in this if you see here penstock is connected, and this is the casing, outer casing. The water is coming out, coming from outside to inside. Okay, now this is outside and it's coming to inside. Gradually this area also will be decreased and the water will become inside through these veins. So these are fixed veins. Or you can say it is guide veins. This will guide the water which is coming outside and let it goes inside to this one. Okay, that's why this is the center of the turbine. So it's the water is coming out from outside and it's moving to the inside of this one. That's why it is called inward radial flow turbine. Similarly, the next one is outward radial flow. So outward radial flow also opposite to this one. So here in this part, the water enters at the center. Here, water enters at center. Directly at the center, the water will be enter, and that will flows radially outward to the. That will flows out, and it will be goes, okay, radially outward. The outward periphery of the runner. That means, now say this is the example actually. The example of this turbine is, I'll give you the name, that is Fournier-Run turbine. Okay, so this is the example of Fournier-Run turbine. Now here at the center of this part is there. This is the suppose center of the part is there. So the water will be directly striked here, and these are the veins are connected to this. Okay, these are the veins, or these are the like this is the runner part. If you consider these are the veins are there. So through these blades it will go to the runner, and outer periphery it will be goes out. Okay, so the water will be leaves this one through the outer periphery of the runner. Okay, that's why it is called outward. From inside to outward it will go, but other one outside to inside, that inside, that is called inward. Okay, and next one is axial flow turbine. So axial flow is very simple. The flow of water actually that will flows through the runner. Okay, along the direction parallel to the axis of the rotation. That one is parallel to the axis of rotation. Parallel to the axis of rotation. Okay. And what is the example of this axial flow turbine is? This one, axial flow turbine is, the example of this is, you can say, like propeller turbine. This is propeller turbine, or we can say Kaplan turbine, or Zonewald turbine is there. So many turbines are there in this. Mostly Kaplan and propeller is to use. So what is the difference between propeller turbine and Kaplan turbine? They both are same, but propeller turbine is having only blades are fixed. Here blades are fixed, and here blades are can be changeable. Okay, that is the difference between propeller and Kaplan turbine. As I told you, the axial flow turbine. So here, if you see, this is the Kaplan turbine actually. Okay, or you can say axial flow turbine. What I told you, that the flow of water through the runner, the flow of water through the runner actually. Okay, that wholly, or we can say, it is to move parallelly. It is to move parallelly to the axis of rotation. So how it is, like how it is taking rotation, this flow direction of water also will be parallel to the axis of rotation of the runner. Okay, so water used to come through the casing part, like from the outside penstock, then it goes inside and it used to strike here axially. So this is a shaft part is there. Okay, so this is axial turbine. Well, we'll discuss in details of Kaplan turbine, then we'll see how it is moving in that. The next one is mixed flow turbine. So mixed flow turbine is slightly, it is mixing, like both will be there. Both in the sense, the water enters the runner. The water enters the runner, okay, from the outer periphery. From the outer periphery in the radial direction. Outer periphery in the radial direction. Okay. And it is entering to this, to the outer periphery of the, we can say, runner. And how it is leaving? So leaving time, it used to leaves the at the center, leaves at the center, and that is direction parallel to the, when it is leaving, it is parallel to the axis of rotation. Axis of rotation. Okay. Axis of rotation of runner. Like how the runner is rotating, along with that, flow direction, like the water which is coming out from that, it will be parallel to the rotation of the runner. Okay. So this is called mixed flow turbine. So what is the example of this mixed flow turbine is nothing but modern Francis turbine. Here we can write, this is modern Francis turbine. Okay. So this is about mixed flow turbine. Mixed flow turbine I have shown you already here. This is actually mixed flow turbine. The water is to come out from here, and after striking here, okay, from this exactly center, this is the shaft part. This is the shaft here. So when the water after striking here, after processing completed here, directly it will come out like from here parallelly. Okay, it is coming inside radially, going outside parallelly of the axis rotation of the runner. That's why I used to tell. So now the next one is according to the head at inlet of the turbine. So head part is very simple. High head, low head, medium, like high head, medium head and low head. So in the high head, low head, medium head, it will have a range is there. So I'll tell the range according to the head. According to the head of the turbine. So high head are capable actually, which can work under very high head conditions, like from several hundred to several thousand or few thousand of meters it can be worked. So high head means in the sense the above 250 meter. The turbine can work above 250 meter. Okay, range, or up to a range of, we can say, like 70 meter. This is one range they have given actually. Up to this range it can work, or it is near about like 6,000 feet near about it will be there. And what is the example of this high head? This is about the high head, and example of this is Pelton. Example of this is Pelton turbine. Similarly, the medium turbine will be there. The medium turbine, which is to work in between, the range of this turbine is 60 meter to 250 meter. Okay, because every turbine is having some range. So some turbines can work in high head, some turbines can work in the medium head. So this is the medium head range. So what is the example of this medium turbine is Francis turbine. This is Francis turbine. And the low head turbine. So low head turbine is actually which is work. This is less than 60 meter. Which is work more than less than 60 meter. That is nothing but Kaplan turbine. That is nothing but Kaplan turbine. This is all about the head. Next is according to the specific speed of the turbine. So specific speed of turbine, low specific speed, medium specific speed, and high specific speed. Now the specific speed, the specific speed actually, if you consider, it is the speed of geometrically similar turbine which can develop 1 kilowatt of power under working 1 meter of head. 1 kilowatt of power can be developed at 1 meter of head. That is called specific speed. So here also first one is low. So low specific speed is we can say when the specific range is 10 to 35. The range of low specific speed is 10 to 35. What is the example of this? That is Pelton turbine. And medium specific speed. So everyone having some range is there. So medium specific speed, the range is actually. So here also sometimes used to call up to 60 also. Up to 60 also it used to call. Okay. So the value will be up to 60 also can be considered. Now medium specific speed actually, the specific speed should be supposed to be 60 to 400. And this is example of this is Francis. And similarly high specific speed. In the high specific speed, obviously it used to work more than 400. This is 400. Okay. Here it is greater than 400. And what is the example of this? Obviously Kaplan turbine. Kaplan turbine or propeller turbine also can be considered in this. So these are the types of turbines are there of different types of turbine. If you want to just summarize this, I'll give a just summarize of this briefly. So here we can write our energy at the inlet we have discussed, and flow direction we have discussed, and head we have discussed, and next one is quantity of quantity of water I have not mentioned it, and another one is specific speed. So one more things I have missed here, that is quantity of water. So the quantity of water also is a very important thing here, which is similar to reverse of this head. So when we discussed it is high head, so that will be opposite to the quantity of water. Here for the Pelton turbine, this is to discharge less quantity of water, and it is obviously medium quantity of water, and here high quantity of water it is to discharge. Okay, high Q, medium Q. So here just I want to give a brief of this energy level, and what are the different turbines we have considered. Just I'll write basically we have taken only three. So one is Pelton, and second one is, we can say this is Francis, and next one is this is Kaplan. So as per the inlet energy inlet, this is coming under impulse turbine. And these two are coming under reaction turbine, what we have seen. According to the flow, we have seen this is tangential flow, and Francis is coming under mixed flow. Even Francis 2 are there, old Francis turbine and new Francis turbine, modern Francis turbine. This is axial, Kaplan is axial. And in the head, it is high head, what we have seen. Obviously this is medium, and this is low. And quantity of water, this is quantity of water or discharge of water, reverse, low, medium will be there same, and here it is high. So mostly for high discharge of water we used to use Kaplan turbine. Specific speed again same thing, low, this is medium, and this is high. This is all about the summary of these different types of turbines. Basically we used to use these three turbines. We'll see in our future lectures how it is working. So I hope you understand this lecture of classification of turbines. If you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.